Good morning, everyone. It is my pleasure to present this paper on vegetation cover effects on outdoor thermal comfort around high-rise developments. A case study of Havelock City, Colombo, Sri Lanka at Faru 2021. People are dreaming to live in jungles filled with greenery. Instead, they will have to live in concrete jungles surrounded with high-rise structures. Introduction of vegetation cover to the urban environment is a very popular practice at present. Assessing the vegetation cover effects on outdoor thermal comfort is the key objective of this research. With the increase in population in urban areas, high-rise development growth is also very high. They consume so much of resources and energy compared to the low-rise buildings. It is a common practice to utilize vegetation cover vertically and horizontally. Strategies such as green facades, green roofs, tree cover, and open green spaces are the usual forms of vegetation cover. Usage of vegetation-based strategies can be seen in modern world in order to minimize resource usage in high-rise buildings and meet sustainable credentials. It is shown that the impact to the solar radiation and albedo, urban geometry, wind flow, pollutant dispersion, and etc. is negatively affected due to high-rise developments. In most instances, vegetation cover acts as an aesthetical element and maintenance is difficult. The studies of these strategies on high-rise developments in tropical zones are limited, and there is a gap with the studies on thermal comfort and vegetation cover-based strategies in outdoor microclimates. This research questions the optimum cover of vegetation and level of impact which can be accomplished through the vegetation cover strategies in order to achieve the optimum thermal comfort. Main objective of this research is to quantify the effect of vegetation cover on outdoor thermal comfort, taking the Havelock City in Colombo, Sri Lanka as a case study and simulation model. This will determine the optimum vegetation cover percentage for thermal comfort. Selected site, Havelock City, which is situated in Colombo, Sri Lanka, which is a residential high-rise development with 8 residential towers. The reason for selecting this tower is to understand the actual behavior of thermal comfort factors within these types of sites while taking this as an example. Vegetation was introduced horizontally and vertically, and cover percentages has been gradually changed. NUF software, which is a holistic modeling software, and it is designed to simulate 3-dimensional microclimate models with surface, plant, air interactions in the urban environment was used for the simulations. This software can calculate fluid dynamics characteristics such as air temperature, relative humidity, wind speed, wind direction, mean radiant temperature, global radiation, turbulence, and thermodynamic processes in ground surfaces, walls, and plants. There were limitations such as limited size of simulation area due to technical capabilities, also inability of detailing finer details, which is smaller than 0.5 meters in size, and another barrier. But the software is sufficient to run the microclimate-related simulations. Wall materials, roof materials are assumed as same for all the buildings. Light absorption, reflection, and diffusion from building surfaces, embodied energy, specific building materials, and energy consumption rates of the building are assumed as equal for this simulation. The scope of the study is limited to the immediate microclimate context around high-rise developments with a special emphasis to the Havelock City, Colombo. Input weather data have been validated with the actual measurements on site. The simulation has been done for the hottest day of the year. So let's move to the findings. Before that, let's talk about the simulation metrics. There are 6 receptors were placed according to the orientation and building distribution. Simulation matrix is created with 5 models, which covers 0%, 25%, 50%, 75%, 100% of their surface area with vegetation respectively. Vegetation type and building materials for all the 5 models were assumed as the same for all simulation models. So let's go for the findings and analysis. Impact on mean radiant temperature with the vegetation cover. Increase in vegetation shows significant warming in the nighttime hours, while there are minimal changes in daytime hours. For all cases, the increase in vegetation cover creates a negative impact with the warming effect rather than a cooling effect that is usually expected. Impact on predicted mean watt. Predicted mean watt is always beyond the defined neutral or comfort threshold value of 0. Therefore, the microclimate around the development is slightly hot. Impact on wind speed. In order to identify the reasons for results above, which do not adhere to the expected norm, wind speed is mapped for a comparative analysis. Built morphology of the development creates a significant wind shadow in certain areas. It can be concluded that when wind speed diminishes, the radiation dissipation, especially at night, is curtailed, thus heat is trapped. According to the analysis, there is a little or no influence from change in the vegetation cover, but the built morphology and the zones the high-rise blocks create are distinct and thus significantly impact the level of thermal comfort. Key findings and implications for design. Vegetation cover changes utilized in the high-rise development of Havelock City have little or no impact in the daytime hours of the day. Impact of building morphology is more significant than the vegetation cover effects as per this finding. The greatest impact of vegetation cover changes on outdoor thermal comfort is seen in the nighttime hours, albeit negative. Radiation loss in nighttime is closely related to the sky view factor, where low sky view factor values are encouraged during the day for shade and high sky view factor values are explored for nighttime radiation loss. Factors such as built morphology and therefore shading potential have significant impact, yet the shading impact of increased horizontal and vertical vegetation cover is seen to be negligible. Morphology of the development demonstrates shaded zones that are comparatively cooler. The correlation of wind speed around the development together with the increased vegetation cover have a negative impact on nocturnal outdoor thermal comfort, where it is shown that where wind speed is low, the potential for those zones to lose heat is diminished, thereby creating warmer areas than those that experience higher wind speeds. Because although we expected positive impact on nocturnal heat loss due to vegetation cover, lack of proper wind intensity and wind shadow zones turns the canopy layer of vegetation cover into an obstacle which disperses the heat loss. Outdoor thermal comfort levels for all cases were found to be above the threshold values for human comfort. This was shown to be true for both daytime hours and nighttime hours of the specific day. Simulation was scheduled to the hottest day of the year, as well as the selected site is classified under local climate zone 1, in other words, compact high-rise developments. Previous research shows that this area can be hotter much as 4K warmer. Thus, a clear indication of the high-rise typology as a key driver of the urban heat island phenomenon. So, as the conclusion, the study presented a research flow that encompasses mapping of impacts of vegetation cover, both horizontal and vertical, on outdoor thermal comfort. This was carried out to better understand the possibilities to minimize the impacts of high-rise developments in the warm, humid climate context of Colombo, Sri Lanka. The researchers highlighted the fact that, contrary to established knowledge on the influence of vegetation integration to ameliorate urban warming and enhanced outdoor thermal comfort, vegetation cover had a little or no impact in the daytime, while the strategy had distinct negative impacts in the nighttime. The findings underline the causative impact of the high-rise typology as a contributor to urban heat island intensity. So that's the end of my presentation. I would like to convey my sincere thanks to Dr. Senaka Dharmasilaka and Dr. Arosha Gamagi, who helped me with the resources during my resource process. At last but not least, I would like to convey my gratitude to all of my year masters of Bachelors of Architecture degree program and fellow colleagues who supported me during this effort. Thank you very much.